Okay, what I'd like to do now is do another example using calculus. And again, our physics class is going to be possibly a little bit ahead of your calculus class, but it'll actually help you learn calculus better because you will instantly understand the applications of what you're doing in calculus. So bear with me and be compassionate to yourself. Understand that you're going to get this. It might take a bit, but this is perfect practice to understand calculus as well. Here's the problem we're going to work on. A bullet which is shot from a rifle is pushed by gases expanding inside the barrel. The force on the bullet is not constant. The force depends on the position x of the bullet in the barrel of the gun and is given by the equation f of x equals negative 21,000x squared plus 10,000x plus 1,000, where f of x is in newtons and x is in meters. The question is, how fast is the 20-gram bullet moving when it leaves the 0.5 meter long barrel? Well, the first thing to always do in any problem is to draw a picture so we can figure out what the heck's going on. So we've got a gun right here, which I'm just going to draw like this. And the bullet is, let's say the barrel starts right there. The bullet's right there. What's going to happen, there's an explosion here due to the gunpowder in the bullet, and that will cause this bullet to have a force exerted that way. But the force is going to change. As this burns up and gets hotter, it'll expand faster. And when it's over here, when the bullet's over here, the force will be less because it will, the gas will be already expanded and there's a lot more room in the barrel over there, so won't be as great. The force won't be as great. Now what I've done here is I've actually used a program to graph this function. So this is a graph of f with respect to x. And a couple things we're not going to consider is this part over here. We don't have to count that because that's when x is negative. We're going to call this point right here 0. X equals 0 right there. So the bullet is never in negative territory. It's also going to leave the gun right when it hits the end of the barrel, which is right here. So we don't have to consider any of that either. So we don't have to worry about any of that part of it. The only part we have to look at is what's right here. In other words, we want to figure out the work done. If this is F, this is X. We want to figure out the work done. In other words, the area under the F versus X curve from 0 to X equals 0.5 right there. So the way we're going to do this now, we could estimate this with just estimating the area under that curve, but we can find exactly how much work has been done by using calculus and finding the exact area under that curve. What we are effectively doing when we use calculus is we're adding up an infinite number of little rectangles, which all these rectangles have the on the base as an infinitesimal dx, and the height will be the value of f for that value of x. Base is dx, height is f, and we're going to add up all infinity of those. Of course, there'll be different heights, but all be with dx. We're going to add up all infinity of those using calculus. And here is how we do that. Let's take a look at our function. It is, f of x is this, so here's what I'm going to do. I'm going to show you what this is. The work done by the gases on the bullet is going to be the integral, also called the antiderivative, really just the area under the curve, from x equals 0 to x equals 0.5 meters, which is over here. This is x equals 0.5 meters. And to do that, this symbol means antiderivative or integral. We just write the function right here, which is negative 21,000 x squared plus 10,000x plus 1,000. Now you will learn more about how to integrate, but it's really just the opposite of taking the derivative. So to integrate this, in this s integral sign, it means sum because we are literally summing all the areas under the curve. We're summing all of these little areas. Here's another one right here. We're summing all infinity of these areas till we fill that whole area up. So here's how we do integrals. It's the opposite of differentiation. So instead of making that go down by 1, you're going to make it go up by 1. And instead of multiplying by that, you're going to divide by that new exponent when we're done. So what we get is the integral from x equals 0 to x equals 0.5 is this. You add 1 to that and divide by the new exponent, which is 3. So it becomes x, it's negative 21,000 x cubed. We add 1, and then we divide by that new exponent, divided by 3. Plus, the integral of that is just, we add 1 to that, so that'll be x squared, so 10,000 x squared over 2. And then when we do this one, you just get 1,000, and we add 1 to x to the 0, that'll give us 10,000x, that's x to the 1, divide by 1, you're there. And then we show that we're going to evaluate this between our limits with a line right there that goes from x equals 0 to x equals 0.5. Now I'm going to leave out the units for ease here. Now what this means is all we got to do is evaluate the final value of this integral, which is with x equals 0.5, and subtract the initial value of this integral, which is with x equals 0. It's always final, where it ends up, minus initial, where it started off. So let's go ahead and do that. All I got to do is do the final. I'm going to plug in this number right here. All I'm doing is I'm plugging in this value for x into this equation. That'll give me negative, and 21,000 over 3 is 7,000, so negative 7,000 times 0.5 cubed plus 10,000 divided by 2 is 5,000. 5,000 times 0.5 squared plus 1,000 times 0.5. You're just plugging in that final value. From that, I subtract the initial value. So this whole thing's in parentheses. So that'll be minus x equals 0, or that's easy. That's just 0. X equals 0 for this one. Well, that's going to be 0. And again, I get x equals 0 there. So minus nothing. So it's kind of easy when I have x equals 0 being my initial thing, because this will all add up to nothing right there. So what I'm getting is this. So let's go ahead and plug this all through. And what this gives us is negative 7,000 times 0.5 cubed is 0.125. Plus 5,000 times 0.25 plus 1,000 times, because that's 0.5 squared, 1,000 times 0.5. And then minus 0, that ain't going to change it at all. And when I do all the math here, what I get is 7,000 times 0.125 will give us negative 875 plus, this will be 1,250, and then plus 500. And when I add all these up, what I end up with is the number positive 875. That's what that all adds up to. So the total work done, in other words, the total area under this curve, this whole area with F in newtons and X in meters adds up to 875 joules. So how fast is the bullet going after that? Well, I know that the work done is the change in kinetic energy, and that means that the work done equals K final minus K initial, and we're assuming the bullet, of course, started from rest, so that goes to 0. So that means that the work done, 875 joules, will just be the final kinetic energy. So I know that the final kinetic energy, work done, is going to equal my final kinetic energy, which is 1/2 mv final squared. Let's go ahead and solve that for v final. I get v final equals, just doing the math there, you're going to get v final equals 2 times the work done divided by m, and take the square root of it, which is equal to the square root of 2 times 875 joules divided by the mass of the bullet, which I must put in SI units. The mass is 20 grams, so that's 0.020 kilograms. So when you're all done with this, you get 296 meters per second. Problem solved. All right, you guys can jam on this. You're going to be learning a lot of calculus during this period, so be kind to yourself, be nice, and don't forget, physics is easy when you do it freestylistically. All right, have a great one. See you next time.